Hello everyone. So far we have discussed about the matter, nature of matter, atomic structure in our previous lectures, right? Yes. Today we'll start a new concept, that is the periodicity of elements. We know that there are plenty of elements, right? And how are these elements classified? How are they grouped? All this we'll be discussing in this chapter about the elements, their periodicity and the trends, how they're placed in the periodic table, etc. So, in around 1800s, there were hardly like 31 elements known. And in around 1829, there was a scientist named Dobriner who came up with something that nobody had done so far. So he was the first one to come up with the trends in the periodicity of elements. So what he did was, he took some elements and grouped them among three. And he said that among this group of three elements, the middle element had the atomic weights in between that of the first element and the third element. And it's just not the middle element, and it's just not the atomic weights. Even the properties of the middle element were in between that of the first and the third elements. But what happened was, this had a lot of drawbacks. It was applicable only to few elements. So they concluded saying that it's just a coincidence and it's not real. So then many scientists were working on this, and around 1865 to 70 there were around 68 elements known. And one more scientist, that is Alexander Newlands, came up with one more idea, that is the law of octaves. Octaves means 8. So what he said was, when he grouped the elements, and he said that the first element and the 8th element had the resemblance in their atomic weights. So he grouped the elements according to their atomic weights. And the 8th element resembled the first element for their atomic weights and the properties as well. But even this had a lot of drawbacks because it couldn't be applied to most of the elements, and it was applicable only till calcium. And then two new scientists, Mendeleev and Mayer, came up with a whole new idea. So what they did was, they arranged these elements in the increasing order of their atomic weight, and they saw the similarity in the physical and chemical properties at regular intervals. So what Mayer did was, he collected the atomic weights of all these elements, and what he did was, he plotted it against the physical properties like atomic weight versus boiling point, atomic weight versus melting point, and he saw a regular pattern, repetition in the pattern of all these. Although Dobriner was the first one who came up with this idea, that is trends in the periodicity, Mendeleev was the first one to postulate a law wherein he said the properties of the elements are the periodic functions of their atomic weights. So what Mendeleev did was, he made a table wherein he arranged all these elements in rows and columns, that is horizontal rows and vertical columns, such that every column had elements which had similar properties. So now what happened was, when Mendeleev was filling all this in the periodic table, he noticed that there are few places where he left gaps, because he noticed that there were elements missing in this periodic table. And he said that not all the elements present in the nature have been discovered yet. And this gave rise to a lot of discoveries as well. And this is the main thing which gave rise to the modern periodic table. And now we'll discuss about the modern day periodic table. In around 1800s, when Dobriner came up with this trends in the periodicity, there were hardly like 31 elements. And then in around 1865, when the law of octaves came, there were around 65 elements. And in the present day, there are around 114 elements. And now we'll discuss about the modern periodic table. Surprisingly, in around 1800s, when all these were happening, there was no idea of this internal structure of an atom. Actually, around 20th century, all these experiments and developments were made related to the subatomic particle. In around 1913, there was a scientist Henry Moseley who observed the characteristic regularities in the X-ray spectra of the elements. And what he did was, he took the X-ray spectra of all these elements and he plotted the frequency versus the atomic number of each element and versus the atomic mass of each element. And he said that in the plot of frequency versus the atomic number, he got the straight line. Whereas in the case of frequency versus atomic mass, he did not get a straight line. So he said that atomic number is most fundamental property of an atom than the atomic masses. And hence, since he said that the atomic numbers are more fundamental than atomic masses, there were changes made in the Mendeleev's periodic law, and this led to what is modern periodic law, and it states that the physical and chemical properties of elements are the periodic functions of their atomic number. Hence, the modern day periodic table is called the long form of the periodic table, and it consists of horizontal rows and vertical column. Mendeleev had named the horizontal rows as series and the vertical column as groups, but in the modern day periodic table, we call these horizontal rows as periods and the vertical columns as groups. And all these groups, the elements in the same group had the same outer shell electronic configuration. For example, if the outer shell electronic configuration is S1, all the elements of the same group had S1. And if it was S2, all the elements of the same group as S2. That is the outer shell electronic configuration. So, altogether, there are 7 periods. Periods means horizontal rows, right? So, in the modern day periodic table, there are 7 periods. And the periodic number is obtained from the highest principal quantum number of the elements present in that period. So, if the elements have the highest principal quantum number like 4s2, then the period is 4. Fine. The first period contains 2 elements. The second period contains 8 elements. The third period contains 8 elements. And then it is 18, 18, 32. And the last period, that is the 7th period, is still incomplete. Classes, we discussed that the electrons in the element of an atom of an element is characterized by 3 different quantum numbers. And mainly, the principal quantum number defines the main energy level known as shells. And we also discussed about the filling of electrons into the subshells, or also called as orbitals. And the filling of electrons into these subshells is called the electronic configuration, right? And the element's location in the periodic table can be known by the electron filled in the last orbital of that element. So basically, a period indicates the value of n for the outermost or the valence shell where the electrons are being filled. Say for example, if you consider any period having n value 3, the next period, that is the successive period, will have the n value 4, that is the one more than n. When we talk in deep about these periods, we will be coming across what is called as 3D transition series. We have that basically have electronic configuration from 3D1 to 3D10. And then we have 4D transition series, and we have 4F inner transition series, which has lanthanides, actinides, and we'll be discussing about all these in detail in this chapter. And when we talk about groups, groups contains elements having the same valence shell electronic configuration, and then they have similarity in the chemical properties, and this is mainly because of the same number and the same outer electronic configuration as well. And then we'll see how the periodic table is divided into 4 different blocks, that is S block, P block, D block and F block. Now let us discuss about S block elements. S block elements basically has 2 groups of elements, that is group 1 elements, which is called the alkali metals, and group 2 elements known as the alkaline earth metals. And they have the outer electronic configuration like NS1 and NS2. And all these metals are highly reactive and they have low ionization enthalpy. And they readily lose their electrons to form ions. In case of alkali metal, they lose 1 electron and form +1 ions. And in case of alkaline earth metals, they form +2 ions. And the metallic character and the reactivity of the elements of this group increases as we go down the group. And because of their highly reactive nature, it is very hard to find these elements in their pure form. Let us discuss about P block element. P block element consists of elements comprising of group 13 to group 18. So all these elements from group 13 to 18 are called P block elements, and these S block elements and P block elements are together called representative elements, or they are also called main group elements. And the outer electronic configuration of this P block elements is NS2, S orbital is completely filled, and NP from 1 to 6. P orbitals can accommodate 6 electrons, right? So it can fill the NP orbital from 1 to 6. And there's something called noble gases, which are at the end of the P block elements, and they have this NS2 NP6 outer electronic configuration, and hence they are said to be stable because it is hard for us to remove an electron or add an electron into those, because they have this complete electronic configuration NS2 and NP6. So now preceding these group 18 elements of noble gases, we get one more group, that is the group 17, and we call them halogens, and group 16 we call them chalcogens. And all these group 17 and group 16 have highly negative electron gain enthalpy. That is, they are ready to gain 1 or 2 electrons in order to attain stability. So that they'll be completely filled and they'll be stable, right? Everyone wants to attain stability. So they have highly negative electron gain enthalpy. And the non-metallic character of the p block elements increases from left to right as we go across the period, and the metallic character increases from top to bottom as we go down the group. Next, let us discuss about the d block elements. These are the elements from group 3 to 12, and the electrons in these elements are filled in the inner d orbital, and hence the name d block elements. And they attain the they have the outermost electronic configuration, that is n-1, d1 to 10 and ns 0 to 2. Fine. And these d block elements all are metals, and they form colored ions. They show paramagnetism, and they exhibit variable valencies, and they form catalyst as well. And except for few d block elements like zinc, cadmium and mercury, which have the electronic configurations, that is n, d10 and ns2 configuration, these elements have properties different from the rest of the d block elements. And in some way, these d block elements form a bridge between the highly active s block elements and very less active group 13 and 14 elements of the p block, and hence they are called the transition elements, because there is a transition from highly active metals to the non-metals of the p block elements. So now let's discuss about f block elements. The two rows of elements at the bottom of the periodic table are called f block elements, and in f block elements the electrons are filled in the f orbital, and hence the name. So the outer electronic configuration of these elements will be n-2 f1 to 14. F orbital can occupy electrons until 14, right? Accommodate. And n-1 d0 to 1 and ns2. So the outer electronic configuration is n-2 f1 to 14, n-1 d0 to 1 and ns2. And these series are called lanthanide series and actinide series. And all the f block elements are metals, and the actinide series are reactive and they are called radioactive metals. Now, we discussed that the entire periodic table is divided into 4 different blocks, that is S block, P block, D block and F block. Just not this, the elements are also divided as metals and non-metals. Metals are usually on the left side of the periodic table, right, where the S block elements are present. And the non-metals are towards the P block elements, that is on the right side of the periodic table. And these metals are usually solids at room temperature, and they are good conductors of heat and electricity. They have high melting point and boiling point as well. They are malleable and ductile. Malleable means they can be formed in the form of sheets, and ductile is they can be formed as wires. And usually, of all the elements known to us, 78% of these elements are metals. And talking about the non-metals are usually, solids and gases at room temperature. They are very low boiling and melting points, and they are very brittle. They can't be malleable and ductile. And they are very bad conductors they're not good conductors of heat and electricity. And when we go from the left to right of the periodic table horizontally, the transition from the metal to non-metal, it's not just abrupt. There are few elements which have the properties of both metal and non-metal. And these elements are called metalloids or semi-metals. Let us discuss about the periodic trends in the properties of these elements. First, let us discuss about the trends in the physical properties. Physical properties includes like atomic radius, ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity as such. First, let us discuss about the atomic radii. We know that atoms are so small, right? Like they're in the terms of 10 power minus 10 meter, that is angstrom. And the electron cloud around the atom does not have a definite size. So how do you find the size of an atom? It's practically impossible, right? So what we do is, in case of non-metals, what we do is, we take the atoms of the non-metal and they combine to form a molecule having a single bond. So consider you take 2 chlorine atoms and combine them together to form a molecule of chlorine, that is Cl2. And then you measure the bond distance of the chlorine. For example, the bond distance of a molecule of chlorine is around 198 picometer, and then you divide it by 2, which you will get as 99 picometer, and this we call it as the atomic radius of chlorine. And in case of non-metal, we call it as covalent radius. So now let us discuss about the trends in the atomic radii. As we move from left to right in a period, across a period, what happens is the atomic size decreases. Why is it so? As we move from left to right, the atomic number increases, right? So the effective nuclear charge also increases, which means that electrons are more bound towards the nucleus. That is, they are more attracted towards the nucleus. And hence the atomic size decreases as we move across the period. Whereas as we move down the group, the atomic size increases with the increasing principal quantum number. In the case of alkali metals and halogens, as we go down the group, as the principal quantum number n increases, the valence electrons are further away from the nucleus. And this is because the electrons in the inner subshells are shielding the outer shell electrons from the nuclear charges. And hence, as the atomic number increases, the atomic radii and the atomic size also increases. Now, let us discuss about the ionic radii. You know that when you remove an electron from an atom, it becomes a cation. And when an atom gains an electron, it becomes an anion. And the distance between this cation and the anion forming the ionic crystal is called the ionic radii. And the ionic radii also has the more or less the same trend as in atomic radii. But in case of cations, the size of cations are lesser than the parent atom. Because in case of cations, they've already lost electrons, but the effective nuclear charge is the same, right? In case of anions, anions have gained electron and there is more repulsion among the electrons now, and hence the size of the anion is greater than that of the parent atom. And we see that some atoms and ions contain the same number of electrons, and hence we call them isoelectronic species. Iso means same, that is the same number of electrons. For example, consider like O2 minus, F minus, Na plus and Mg plus. All these ions contain 10 electrons, right? But the ionic radii of all these are different because the ionic radii depends upon the charge of the ion, right? So the cation having the larger positive charge will have a smaller radius. Then the anion having the larger negative charge will have a bigger radius, right? Ionization enthalpy. Ionization enthalpy is nothing but the tendency of an element to lose electrons. So it represents the energy required to remove an electron from an isolated gaseous atom which is in its ground state. It requires some energy to remove an electron from an atom, right? Hence, ionization enthalpies are always positive. And further, there are first ionization enthalpy, second ionization enthalpy and third ionization enthalpy and so on. The second ionization enthalpy will be higher than the first ionization enthalpy because removing an electron from an already positively charged ion is difficult from removing an electron from a neutral atom, right? So first ionization enthalpy will be like removing an electron from a neutral atom. But when the atom is already positively charged and you have to remove an electron, it requires higher energy as well, right? We notice that the first ionization enthalpy increases across the period and decreases down the group. And further, we also notice that the ionization enthalpy and the atomic radius, there is some connection between these two. And these two are also dependent on two factors, that is the attraction of the electron towards the nucleus and the electron-electron repulsion and the shielding effect. All this plays a role in this. Next is the electron gain enthalpy. What is electron gain enthalpy? So when you add an electron to a neutral gaseous atom to convert it into a negative atom, that is negative ion, that is an anion, what happens is there will be some changes in the enthalpy. So this is what is called as electron gain enthalpy, the changes in the enthalpy when a neutral atom receives an electron. So this is just a measure of with what ease the electrons get added into a neutral atom. The variation in the electron gain enthalpies for elements is less systematic when compared to the ionization enthalpies. And as we go across the period, the electron gain enthalpies become more and more negative. But as we go down the group, it becomes less negative. Now, let us discuss about electronegativity. We know that during the formation of a compound, two or more atoms of different elements are involved, right? So what these atoms do is they share electrons. Fine. So electronegativity is nothing but the ability of the atom to attract these shared electrons towards itself. So unlike ionization enthalpy or electron gain enthalpy, this electronegativity doesn't have specific values because it totally depends upon the element to which it is bound, right? And this electronegativity increases across the period from left to right, and it decreases down the group from top to bottom. And interestingly, this electronegativity is related to atomic radii. So we know that as the atomic radii decreases, that when there is an attraction between the nucleus and the electrons, there will be a decrease in the atomic radii, right? Hence, electronegativity increases. And when the atomic radii increases, the electronegativity decreases. That is down the group. Further, we know that the non-metallic elements have strong tendency to gain electrons, right? So we can say that as the non-metallic character increases, the electronegativity also increases, and they are related to one another. And down the group, the non-metallic character decreases, right? Because the metallic character increases down the group. So in that case, electronegativity decreases. So now let us discuss about the trends in the periodicity of the chemical properties. First up, periodicity of valence or oxidation states. We know that valency of an element is the most characteristic property of the element, right? And this is given by electronic configuration. So valency is usually the number of electrons present in the outermost shell of that atom. Fine, element, fine. So now how to calculate these oxidation states? What are oxidation states? So consider an example of two compounds, that is OF2 and Na2O. In this case, there are three elements involved, right? Oxygen, fluorine and sodium. So let us see the electronegativity of these three elements. Fluorine is more electronegative than oxygen, which is more electronegative than sodium, right? So when OF2 is formed, fluorine is sharing one atom with oxygen. So the electronic configuration of fluorine is 2s2 2p5, right? It is in short of one electron. So what it does is two fluorine atoms are sharing one electron each with the oxygen. So the electronegativity of fluorine is -1. Fluorine is the highest electronegative atom. Fine. So oxygen gives two pair of electrons to the fluorine. That is, it's sharing two pair of electrons to the fluorine, and it becomes the charge +2. So fluorine is most electronegative. Here fluorine will attain -1 oxidation state, and oxygen will attain +2 oxidation state. Next, in case of Na2O, here oxygen is more electronegative than sodium in this case. Fine. So what oxygen does it shares two electrons from sodium. So oxygen will gain a oxidation state, that is -2. So oxidation state is nothing but the charge acquired by the atom on the basis of the electronegativity which the other atom it bonds to. Fine. Next is the anomalous behavior of the elements of the second period. So we notice that in the second period, few elements do not have the behavior like the other elements. And these few elements are like, from the alkali metals and the alkaline earth metals, they are lithium and beryllium. And the other elements are from group 13 to group 17. These elements do not have the behavior like the rest of the elements in the second period. And usually, metal forms ionic compounds, right? But in case of here, lithium and beryllium, they form compounds with the covalent characters. And interestingly, the behavior of this lithium and beryllium are similar to that of aluminum and magnesium, and this is called the diagonal relationship. And what might be the reason for this difference in the behavior? It might be due to small size or large charge to radius ratio, or maybe due to high electronegativity. And also, this first member of these p block elements like carbon and nitrogen, they form multiple pi bonds with itself and with the atoms of the second elements. Like in case of carbon, they form multiple pi bonds, that is carbon-carbon double bond, carbon-carbon triple bond, or nitrogen-nitrogen double bond. And also they form compounds with oxygen as well, like C double bond O, N double bond O, and C double bond N, etc. So by now we at least have a clear understanding that the periodic properties of all these elements are related to their electronic configuration. So we can say that these chemical properties and physical properties of the elements revolve more or less around the electronic configuration of that element. So as we move across the period from left to right, the atomic radii decreases and the ionization enthalpy increases across the period. So towards the left of the periodic table, the ionization enthalpy is the least, and the electron gain enthalpy becomes more and more negative as we move across the period. So the rightmost element will have the highest negativity of the electron gain enthalpy. So because of these reasons, the extreme ends are highly reactive and the elements in the center are like moderate. So this results in the high reactivities of the extreme ends of the periodic table. When we talk about the extreme left end, that is the alkali metals, they usually give up an electron and become cation. And the extreme right, that is halogens, they usually gain electrons and become anion. And this is further related to the oxidizing and reducing properties, that is behavior of these, and the metallic characters and the non-metallic characters. The elements on these two extremes combine with oxygen to form oxides. And the oxides formed by the metals, that is on the extreme left of the periodic tables, are usually basic. And the oxides formed from the extreme right of the periodic table, that is from halogens, are usually acidic. And all these center elements form amphoteric or neutral oxides. In amphoteric oxide, they behave as acidic in the presence of base, and with the acids they behave as basic. And neutral oxides neither behave like acidic nor basic. And among the 3D elements, the change in atomic radii is much smaller when compared to that of S and P block elements, that is the representative elements. And among the inner transition elements, that is 4F, the change in the atomic radii is much lesser. And the ionization enthalpies are intermediate to that of S and P, and hence this makes them less electropositive than the group 1 and group 2. And further, talking about the metallic character increases down the group and the non-metallic character decreases down the group. So this is all about the periodic properties of the elements and the periodic table. I hope you have understood all these concepts, and thank you for watching. Hello everybody, I hope you are liking this course, and if yes, hit the like button and share it among your friends. And please do subscribe to read my course and check out their other videos as well. There are a lot of interesting videos. And thank you for watching.